Okay, imagine a perfectly smooth piece of copper. Electricity zips through it effortlessly. Or picture the seemingly magical pull of a simple bar magnet.
Yeah.
As physics students, you've probably worked with these phenomena countless times. But have you ever stopped to really ponder why they happen at such a fundamental level?
Right. What's really going on underneath?
Exactly. What's going on with the electrons inside that makes some materials conduct and others attract?
That's the million-dollar question, isn't it? These everyday observations hint at a surprisingly deep and complex world at the microscopic level. And that's precisely where we're headed in this deep dive.
Exactly. We're going to be exploring the very roots of two pivotal ideas in condensed matter physics.
hmm
First, how localized magnetic moments can form in metals, and second, the intriguing concept of electron localization in disordered systems.
And these weren't just minor tweaks to existing theories. They fundamentally challenge the prevailing understanding of solids based on band theory.
Totally. And for anyone serious about understanding the behavior of materials, whether you're diving into advanced solid state courses, maybe considering research, or just want a deeper appreciation for how the world works.
Which, let's face it, is pretty cool.
It is. These concepts are absolutely essential. They unlock the door to understanding everything from superconductivity to the behavior of semiconductors. Get ready for some real aha moments.
Hopefully, that's the goal.
Our roadmap for this journey is the Nobel Lecture delivered in 1977. This lecture gives a first-hand account of how these revolutionary theories were developed.
A great primary source. So let's tackle the first big puzzle. The emergence of local magnetic moments in metals.
Okay.
Before the groundbreaking Anderson model, band theory was really the dominant framework for understanding solids. It explained a lot, but magnetism in metals, that was a particularly sticky problem.
Because with band theory, you picture electrons as being delocalized,
Sure.
right? Roaming freely through the crystal lattice. So it's hard to see how a stable, localized magnetic moment could even exist in that picture. Things seemed clearer with insulators, like Mott insulators.
Precisely. In Mott insulators, there's a significant energy cost, usually call it the Hubbard U, to have two electrons occupy the same atomic site.
Right, that Coulomb repulsion.
Yeah, and this U energy is much larger than the kinetic energy associated with electrons hopping between sites, sometimes called B. As Kuhl's initially suggested and Mott elaborated, this strong on-site repulsion basically forces electrons to stay put.
Leading to insulating behavior.
And the possibility of localized magnetic moments, you can think of it like dn plus dn requiring a large energy U to become dn1 plus dn plus 1.
Okay, so with metals where electrons are mobile, you wouldn't expect this strong localization. But experiments, well, they threw a wrench in the works, especially when looking at superconductivity.
Absolutely. Matthias and Sewell at Bell Labs were key players here. They observed that adding even tiny amounts of certain magnetic impurities,
Like what kind?
some rare earth elements or transition metals like iron, say in molybdenum, cause a dramatic drop in the superconducting transition temperature. To your
Right. T-tier, the temperature below which it becomes superconducting.
Exactly. And you can see this in Figure 3a from the lecture. It's like these superconducting materials had a severe reaction to these magnetic impurities.
Okay, but here's where it gets really intriguing. In other scenarios, like putting iron into titanium, as shown in Figure 3b,
Yeah.
adding iron had little to no impact on TC, or in some cases, even seemed to increase it.
The same magnetic atom behaving in completely opposite ways depending on the host metal. Wild.
Totally wild.
Exactly. This led to systematic investigations, like the work by Clogston and his colleagues, trying to figure out, when does an impurity atom actually show a magnetic moment when you dissolve it in a metal?
Because the basic electronic origin of that magnetic moment in a metal wasn't really understood.
Not at a fundamental level, no.
So before Anderson, what were the ideas floating around trying to explain this?
Well, Van Vlick and Hurwitz had already pointed to the importance of the on-site Coulomb interaction. Even in metals. That wasn't totally new.
Okay.
Then, Friedel and Blandin introduced the concept of resonant or virtual states associated with the impurities.
Virtual states.
Yeah, instead of seeing the impurity as just an isolated atom, they proposed describing it in terms of how it scatters the conduction electrons, and crucially, different scattering for spin-up versus spin-down electrons.
Ah, spin-dependent scattering.
Right. And the 1959 Oxford Conference was apparently a pivotal moment where many of these sort of nascent ideas came together.
It sounds like a lot of insightful qualitative reasoning, but maybe lacking a concrete underlying electronic mechanism.
Precisely. On the experimental side, Researchers like Owen, Zimmerman, and Yosida took a more empirical approach. They basically said, okay, let's just assume there's a localized atomic spin S at the impurity site.
Right.
And let's say it interacts with the surrounding free electrons through some exchange interaction J.
Which gives you the Kondo-Hamiltonian.
Exactly, that NASJS callus term, where is the conduction electron spin density.
Hmm.
While this Hamiltonian was useful for describing some things, it was more phenomenological. It didn't explain where that local spin S came from in a metal in the first place.
Okay, so enter the Anderson model. How did it provide that fundamental explanation?
The Anderson model, introduced in 1961, was the first clear electronic mechanism for a local magnetic moment existing in a metal. It took that crucial on-site Coulomb interaction U,
Hubbard U?
right, and explicitly included an additional localized orbital at the impurity site. This orbital has its own electron occupancy and an accretion operator, CDOL.
Okay.
And crucially, it also incorporated a term describing the tunneling of electrons between this localized d orbital and the conduction band states. That's the VDK term. The full Hamiltonian is right there in equation 4.
This VDK term, you mentioned it represents tunneling through a centrifugal barrier. Can you give us physics students a visual for that?
Sure. Imagine the electron in the impurities d orbital trying to mix with the free electron states in the host metal. There's this effective energy barrier. You can sort of picture it like a centrifugal force that hinders direct mixing.
Okay.
VDK basically quantifies the probability of an electron from that d orbital tunneling through this barrier and becoming part of the conduction band, or an electron tunneling back the other way.
Quantum tunneling.
Exactly. And this tunneling process leads to what Friedel called resonances, or virtual bound states. You can visualize it as a broadened energy level for the impurity sitting within the host metal's band structure. Figure 4 shows this nicely.
And the width of this resonance.
That's a Mandy, given by equation 5. It's directly related to how strong the tunneling is, so VDK squared, and the density of states of the host metal at that energy.
So if we just had this tunneling, VDK, without the on-site Coulomb repulsion U, would just have a broadened impurity level, right? And any potential moment would be washed out by the free electrons mixing in.
Precisely. No magnetism there.
So where does the magnetism actually come from in the Anderson model?
The key insight is how U, the Coulomb repulsion, dramatically alters this picture. A relatively straightforward approximation, the Hartree-Fock method, applied to the Anderson-Hamiltonian, revealed something really interesting.
What was that?
If the energy of the impurity D level, Ed, is sitting somewhat below the Fermi level, EF.
Which you can think of as the highest filled energy level at zero temperature.
Right. And if the ratio of the resonance width to the Coulomb interaction EU is small enough, then that single impurity level actually splits into two spin-polarized resonances. Figure 5 shows this.
Spin polarized, meaning one for spin up, one for spin down.
Exactly. You end up with, say, a predominantly occupied spin-up state below the Fermi level and a largely unoccupied spin-down state above it, or the other way around.
Ah, so the Coulomb repulsion U is stopping two electrons from piling onto that D level, and because of where it sits relative to the Fermi level, it's energetically cheaper to fill one spin state more than the other.
You got it.
Which gives you a net imbalance of spin, a local magnetic moment at the impurity.
Precisely.
And these aren't like traditional localized bound states like in an isolated atom, are they? They're more like spin polarized enhancements within the band structure.
That's a great way to put it. They're resonances, not true bound states outside the band. This leads to magnetically polarized solutions, as you can see in the magnetic region of the parameter space shown in Figure 6.
Wow.
And the model could even predict whether a specific impurity in a specific metal would be magnetic based on parameters you could estimate. It was remarkably elegant and powerful, moved way beyond just describing things phenomenologically.
And the Anderson model deliberately simplified things, right? Ignored crystal structure details, the full degeneracy of D levels. Why was that simplification okay?
Well, that's a crucial aspect of theoretical physics, the art of building effective models. You don't always aim to perfectly replicate every single detail of reality.
You want the essential physics.
Exactly. By focusing on the most critical interactions, the U, the ED, the hybridization VDK, the Anderson model, successfully captured the fundamental mechanism for local moment formation. The appendix of the original paper did discuss things like D-level degeneracy and orbital quenching, showing the model could be extended.
Okay, so the model explained how local moments could exist. What about the interaction between these local moments and the surrounding sea of conduction electrons?
Ah, good question. That brings us to the nature of the spin-dependent interaction. Even before the Anderson model, People debated whether this interaction should be ferromagnetic, spins aligning, or antiferromagnet, spins opposing.
Right.
The concept of superexchange, which was known from insulating magnetic materials, suggested an indirect interaction, usually antiferromagnetic, mediated through other ions.
Okay.
This implied that an occupied spin state at the impurity, below the Fermi level, would effectively repel conduction electrons of the same spin, while an unoccupied state above EF would attract them.
And did the Anderson model help clarify this interaction in metals?
Yes, Anderson and Clogston showed that the model naturally predicted this kind of indirect exchange interaction, and it was generally antiferromagnetic.
Okay.
Then later, Schrieffer and Wolff provided a really crucial theoretical link. They showed a perturbative equivalence between the Anderson model and the Kondo model.
Ah, connecting the two.
Exactly. They showed how that exchange integral J from the Kondo Hamiltonian, which was initially just put in empirically, could actually be derived from the fundamental parameters of the Anderson model. That's equation 6. It was a major step in unifying these two approaches.
You mentioned the Kondo problem earlier. As physics students, we often hear about the Kondo effect. What exactly was the core of the problem?
Well, both the Kondo model and, by extension, the Anderson model ran into theoretical trouble at very low temperatures.
How so?
Certain calculated physical quantities, like electrical resistivity, showed mathematical divergences. They blew up as the temperature approached absolute zero.
Not physically realistic.
Right. The physical picture that emerged was fascinating, though. As you lower the temperature, or the energy scale, the antiferromagnetic coupling between the local spin and the conduction electrons effectively gets stronger and stronger.
Okay.
Eventually, it becomes so strong that it actually binds an electron with the opposite spin to the local moment. This effectively screens the local moment, hiding it and leading to a non-magnetic ground state at the lowest temperatures.
That sounds remarkably similar to how quarks are confined within hadrons in particle physics, this idea of screening at low energy scales.
It's a very insightful analogy.
Yeah.
Absolutely. The screening of the local moment at low temperatures has real parallels with quark confinement via the strong force. It just highlights the surprising connections you find across different areas of physics.
So how was this Kondo problem finally cracked? How did they get a consistent picture at all temperatures?
The breakthrough came with renormalization group theory, a really powerful technique pioneered in this context by Kenneth Wilson. You can see a schematic of his results in Figure 7.
Renormalization groups sounds intense.
It is. But the basic idea is to study how the effective parameters of your system change as you change the energy scale or temperature you're looking at. Wilson's work provided a non-perturbative solution. It didn't rely on small parameters to the Kondo problem. It correctly predicted how things like magnetic susceptibility should scale with temperature and got rid of those nasty low-temperature divergences.
And did it further cement the link between the Anderson and Kondo models?
Absolutely. Krishnamurthy performed numerical renormalization group calculations directly on the Anderson model, shown in Figure 8. The results were in remarkable agreement with Wilson's solution for the Kondo model.
So they really were describing the same physics.
Fundamentally, yes. Haldane even derived precise mathematical relationships between the parameters of the two models, equation 7, allowing you to quantitatively map results from one end to the other.
Wow. It sounds like this period was a real intellectual whirlwind in condensed matter physics.
It truly was. Anderson mentions in his Nobel Lecture, there's this memorable quote. Apparently in Swahili, Kondoism means something like robbery with violence,
Seriously.
reflecting the disruptive and transformative impact these ideas had on the field, just completely overturned existing ways of thinking.
Okay, that's a fascinating deep dive into the story of local moments in metals. Now let's switch gears to the second major topic of the lecture. The origins of localization theory.
Right.
This challenged band theory in a different way, focusing more on the impact of disorder, correct?
Yes, exactly. This story starts back in the mid-1950s at Bell Labs, with a new theoretical department forming.
Okay.
A central focus was trying to understand magnetic relaxation in donor impurities in silicon. This was driven by some really precise paramagnetic resonance experiments done by Fletcher and Ferrer.
What were they looking at specifically?
They were investigating electron spins at very low temperatures in silicon samples that had varying concentrations of phosphorus impurities, specifically in the range where these impurities start to form an impurity band.
These donor impurities, like phosphorus replacing silicon, they each contribute an extra electron, right?
Correct. Phosphorus has one more valence electron than silicon. So when it substitutes, that extra electron is weakly bound to the positive phosphorus ion, forming a sort of hydrogen-like orbital.
Okay.
But because silicon has a relatively high dielectric constant, and the electron has an effective mass in the crystal, this orbital is actually quite large spatially. The effective Bohr radius is around 20 angstroms. Figure 9 gives a schematic idea.
So you have these fairly big overlapping electron orbitals tied to the impurity atoms. What were the initial thoughts about their electrical behavior?
Well, the initial thinking, influenced by Mott's ideas about electron interactions, was that since there weren't many compensating acceptor impurities to trap electrons,
Right.
most donor atoms would just be singly occupied because of that Coulomb repulsion you attached to
Yeah.
use. That would explain the paramagnetic spins they saw.
Makes sense.
Cohn also suggested that any empty donor sites might be sort of pinned electrostatically near the few charged acceptors present. You can see that idea in Figure 12.
Yeah.
The general expectation was pretty limited electron mobility.
But the experiments showed something else.
Well, they did see a subtle speeding up of relaxation times. As the impurity concentration got close to what we now call the Mott-Anderson transition regime.
Okay.
And this led Anderson to suggest to Jabal that they should look at dielectric relaxation in these doped silicon samples.
And that uncovered something unexpected about how electrons move.
Exactly. These experiments revealed hopping conductivity. Electrons were moving, but not in the delocalized band-like states you might have first guessed for this impurity band. Instead, they seem to be hopping between localized states associated with the individual impurity atoms.
Popping. Okay. Now, Ferrer's experiments used ENDOR, electron nuclear double resonance. How did those precise measurements add to the picture?
So Portas had earlier introduced this idea of inhomogeneous broadening in spectral lines.
Right.
You picture the broad line as being made up of many narrower spin packets. Each packet is a group of spins feeling slightly different local magnetic fields, so they resonate at slightly different frequencies within the overall line. Figure 13 illustrates this.
And the lifetime of these spin packets tells you about the interactions between the spins.
Exactly. But the problem was, simple estimates for the spin packet lifetime, based on the interaction strength, G, between neighboring impurity spins and how many neighbor Z's there were.
Given by equation 8.
Right. Those estimates predicted lifetimes that were way, way shorter orders of magnitude, shorter than what Ferrer was actually observing with his very precise ENDOR technique.
So the spins were staying coherent, staying in their packets for much longer than expected.
Yes. Ferrer found these packets remained saturated for significantly longer, indicating much weaker effective interactions than the simple theories predicted. This big discrepancy was a crucial puzzle. Existing ideas couldn't explain it.
And this discrepancy was a key spark for Anderson's all-or-nothing theorem, which grew into his localization theory.
It was a major motivation, yes. Anderson's all-or-nothing idea, which then matured into the theory of localization, was a really radical departure from the standard block picture of extended electron states in crystals.
How so?
He started exploring the possibility that in a disordered system, where the potential energy landscape isn't perfectly periodic because of, say, randomly placed impurities, the electron wave functions might not always stretch throughout the whole material.
They could get stuck.
Essentially, yes. They could become spatially localized, trapped around a particular site or region, even if the energy spectrum itself remained continuous.
So instead of electrons always being able to roam freely through the lattice, even with some disorder, they could actually become trapped in certain areas just because of the randomness.
That's the core idea of Anderson localization. He tried to formulate a rigorous proof for this, though a truly complete mathematical proof was tricky then, and still is in some ways.
And this idea wasn't immediately popular.
No. Initially, this radical proposition didn't get a lot of attention in the physics community. It was quite counterintuitive.
What was the simplified model he used to explore this localization idea?
He used a model called the linearized random tight-binding model for non-interacting particles. That's equation 9.
Type binding, so electrons hopping between sites.
Right. Imagine a lattice where electrons can hop between neighboring sites. The hopping strength, V, representing the transfer between adjacent sites, was taken as non-random, uniform.
Okay.
But the key was the energy of an electron at each site, E. That energy wasn't uniform. It was randomly chosen from some probability distribution with W. Figure 14 gives a picture of this random potential.
So a bumpy, unpredictable energy landscape.
Exactly. And importantly, the C objects in the model could represent various excitations, not just electrons.
So you have this lattice, uniform hopping V, but random site energies vie with W. How did he figure out if the resulting electron states would be localized or extended?
Anderson cleverly realized you could tackle this using perturbation theory in two fundamentally different
Two
ways.
limits.
Yeah, either treat the randomness W as a small tweak compared to the hopping V, or do the opposite. Consider the randomness W to be large and treat the hopping V as the small perturbation.
And the results are different.
Drastically different. The behavior of the perturbation series diverged in the two limits, pointing to qualitatively different physics.
And he focused on the case where the randomness was strong compared to the hopping.
Yes. To analyze that, he used the resolvent operator, or Greenian, GE. That's equation 10. It's a powerful mathematical tool that holds info about all the possible energy states and wave functions.
Okay.
Now, the usual way to think about transport in disordered systems starts from the block picture plane wave-like states and treats the random potential as just scattering these extended states. Equations 14 and 15 describe that.
Right, the standard approach.
Anderson's big insight was that even if you have a continuous range of possible energies, the states themselves might not be spatially extended if the disorder is strong enough.
So he flipped the standard perturbation approach on its head. How did his alternative method work?
Exactly. And this alternative perturbation theory, which he kind of jokingly called CISPORT, the random site energies AI are the main unperturbed part. The hopping integrals V are the small perturbations allowing movement. Instead of propagators for free like electrons, he used locators, G, equations 18 and 20.
Locators.
They basically represent the probability of finding an electron at site I with energy E if there were no hopping. By analyzing the series expansion of these locators in terms of the hopping vague, he could find the conditions for an electron to stay localized at a site.
And the condition for localization involves balancing the energy difference between sites against the hopping strength.
Precisely. For an energy EJ to show up as a sharp peak in the imaginary part of G, meaning an electron with energy E, is likely found at site I, you need the energy EJ of a neighbor J to be significantly different from A, and the hopping speed between them can't be too large.
So if it costs too much energy to hop, it stays put.
Kind of, yeah. He also reasoned physically that these localized states would have wave functions that decay exponentially away from their center. Equation 21 shows that. This exponential decay means the electron's probability cloud is confined.
Okay, so if it's energetically tough to hop to a neighbor with a very different energy, the electron tends to stay localized. But what about hopping through a chain of sites that happen to have similar energies, even if they're far apart? Could that delocalize it?
Ah, that's where the higher order terms in his perturbation series come in. They're crucial.
What do they do?
Anderson showed these higher terms effectively renormalize the hopping integrals. They make Vi's decay exponentially with distance, even if the original hopping was just nearest neighbor. They also broaden the energy spectrum.
Okay.
The regime of extended states where electrons can move through the whole system arises when this perturbation theory breaks down. That happens when these renormalized hopping terms can effectively bridge arbitrarily large distances.
And that breakdown point, that's the mobility edge.
Exactly. The mobility edge. It's the critical energy that separates localized states from extended conducting states in a disordered system.
That sounds incredibly connected to Mott's earlier ideas about a minimum metallic conductivity.
It absolutely is. Mott had proposed this idea of a minimum possible conductivity for a metal, suggesting a sharp transition to insulating behavior below that. Anderson's localization theory provided the microscopic mechanism for that transition.
So the mobility edge is the boundary.
Right. Electrons with energies below the edge are localized. They don't contribute to DC conduction at zero temperature. Electrons above the edge are extended and can conduct. The convergence or divergence of the self-energy series in Anderson's math is energy dependent, which naturally leads to this separation.
And presumably the dimensionality of the system matters a lot here, whether it's 1D, 2D, 3D.
Absolutely critical. Anderson's original calculation, though approximate, turned out to be exact for something called a Cayley tree, or Bates lattice, figure 17. That's like an infinitely branching tree structure, no loops, effectively infinite dimensional.
Okay.
Later work, more rigorous math, established that in one dimension, all electronic states become localized by any amount of disorder, no matter how small.
Always localized in 1D.
Yes. And the concept of a critical dimensionality, DC, emerged. Below DC, all states are localized for any non-zero disorder. Tholis's scaling theory later suggested DC might be 2 for this Anderson transition, at least for short-range hopping. Still debated for some cases, but dimensionality is key.
Now, initially, wasn't there some concern that electron Electron interactions, which the simplest Anderson model ignores, might mess things up and destroy this localization.
It was a very valid and important question early on, yes.
Right.
But then people realized that Mott insulators show localization because of strong electron interactions, even without any disorder in the site energies.
Ah, right. You as the driver there.
Exactly. So it became clear that Mott localization, driven by U, and Anderson localization, driven by disorder W, aren't mutually exclusive. They're complementary effects. They can coexist and even reinforce each other.
Which led to ideas like the Fermi glass.
Precisely. That term describes systems where you have both strong interactions and significant disorder, leading to localized electrons right around the Fermi level.
And to really nail this down, there were computer simulations too.
Yes. Very important. Yoshino and Okazaki did some insightful computer simulations, shown in Figure 18. They beautifully illustrated the
What
transition.
did they show?
They showed how the calculated electron wave functions changed dramatically as they increased the disorder strength, WV. You could see the states transition from being spread out over the whole simulated system to being tightly confined in a small region, just by tweaking the disorder strength a bit. A clear visual of the localization transition.
It's quite remarkable, isn't it, that such a fundamental shift in electronic behavior from conducting to insulating can just pop out of randomness at the atomic level?
It truly is profound. And Anderson wrapped up his Nobel lecture with a very fitting quote from Lewis Carroll's Through the Looking Glass. Figure 19 has it. It's the bit about the Red Queen's race.
Oh, yeah.
Now here, you see, it takes all the running you can do to keep in the same place.
Ah, perfect.
It wonderfully illustrates the idea, right? Even with energy available, an electron or a magnetic moment in these disordered or interacting systems can just remain stubbornly localized, unable to really propagate freely. It takes effort just to stay put, in a sense.
So to bring it all together then, this deep dive into the 1977 Nobel Lecture has really shown us two huge things. First, how the Anderson model gave the first microscopic explanation for local magnetic moments popping up in metals, really challenging that simple band theory view.
Right. A huge step.
And second, we've explored how Anderson's theory of localization completely changed how we understand electron transport in disordered systems, showing that, just because you have a continuous spectrum of energies doesn't mean the electrons can actually go anywhere. They might be stuck.
Absolutely.
Yeah.
Both were truly paradigm-shifting ideas for condensed matter physics. Changed the game.
Definitely. And for you physics students listening, getting a handle on these fundamental models, Anderson model for moments, Anderson localization for disorder, it really provides an indispensable foundation. It helps make sense of a huge range of phenomena in solid-state physics and even beyond.
Yeah, they highlight the really intricate and often surprising ways that microscopic interactions and just plain old randomness end up governing the macroscopic properties of the materials all around us.
And it really makes you think, doesn't it? Like, how does the interplay between disorder and strong electron interactions lead to even more exotic states of matter that maybe we're still discovering?
For sure. Lots still to explore there.
And could we maybe harness these localized states, use them in disordered systems for new kinds of technologies? Definitely some fascinating questions to ponder. If you're keen to delve deeper, the original Nobel Lecture and the references cited in it are absolutely invaluable resources.